We always have to have fireworks at the Royal Institution, so go ahead, Bryson, please. Right, there's the first fire. There's the parent fire. The sparks are flying up. It started another one there. That's the daughter fire. And a granddaughter. And a second daughter of this one. But the point is that to the extent that there are any differences between these fires, they do not get their qualities from their parents. There are sparks that flow from fire to fire. All that the sparks do, though, is to start a new fire. Nothing is carried in the spark. There's no information carried in the spark. And this, of course, this is where rabbits and humans and stick insects differ from fires. Don't be misled, by the way, by the fact that rabbits and humans have a mother and a father. Stick insects only have a mother like fires. In this particular respect, stick insects are like fires. But in the important respect that I'm talking about, stick insects do not resemble fires. Because unlike fires, stick insects have true heredity. At least some of their qualities, colour, shape, size, spininess and so on, they actually get from their mother, not only from their surroundings. Something travels from mother to daughter. Something in the spark that travels from mother to daughter, there is information. So what is this mysterious information that eggs contain and sparks don't? Well, it's DNA, this astounding molecule, which contains in the sequence of its bases all the information, or almost all the information that you need to build a stick insect or a rabbit. DNA comes like an ever-flowing river down the generations. The river of DNA that flows through us into the future is a pure river that leaves us exactly as it finds us. With one exception. There are occasional, very occasional, random changes called mutations. Because of these, there is variation, genetic variation, in the population. And that opens the way for natural selection. Those varieties of DNA that just happen to be good at building ancestors, at building bodies that have good eyes, good legs, good anything else, survive. So the world automatically becomes filled with good DNA. This means good at making bodies that are themselves good at surviving. This is the Darwinian explanation for why living things are so good at doing what they do. They're good because of the accumulated wisdom of their ancestors. But it's not wisdom that they have learned. It's wisdom that they chanced upon by luck, lucky random mutations which were subsequently selected. And in each generation, the amount of luck was very small. But because the luck has been accumulated over so many generations, we are impressed by the end product. Now, I want to apply this lesson to three particular cases, three particular problems that have given difficulty: the eye, the wing, and camouflage. And I choose them because they're famously regarded as difficult. First, the eye. Charles Darwin himself said, "To this day, the eye makes me shudder." Creationists are particularly fond of the eye because they like saying, what is the use of half an eye? An eye only works, they say, if every little detail is in place. Until you've got that, the eye won't see anything at all, so how can it possibly have evolved? And even serious scientists have sometimes queried whether there's been enough time for the evolution of the eye. Well, suppose we start with an ancestor who didn't really have an eye at all, but just a single, simple sheet of light-sensitive cells. That's represented by this screen here, and there's a television camera behind looking at the screen so that we on the screen, on the television screen, shall see what this primitive animal would see. So this animal, with hardly any eye at all, will at least be able to tell the difference between light and dark. Light and dark. Now, the next stage in evolution would be to have a shallow cup. This animal would be able to tell the direction that light is coming from, because there a shadow would appear. A shadow would appear there. And if you can tell the direction a light is coming from, then you can tell the direction that a predator is coming from. Now, although we've represented this as a cup coming out from the wall, it would in fact probably be an indentation, and it would be a gradual indentation. It's inconvenient to make a gradual indentation. It has to be made as a rather abrupt cup that comes out 6 inches at a time. But it's easy to see that that shadow effect that we've just been witnessing would work progressively and gradually as the cup gets bigger. Let's make it bigger still now, Bryson. And this cup is even more effective. And if we go on to the next stage where we make the cup gradually bigger again, so big that it becomes just a little hole in the end. Right, now this animal has a very good idea of exactly where the light is, and by the same token exactly where, for example, a predator is. And I think with this eye we might even get a little image. See if we can get an image of Bryson's hand. That smudge there is Bryson's hand, and you can just about see a very dim image of his fingers. So an animal with an eye like this would be able to see perhaps just a little bit what kind of predator it was. Let's go to the logical conclusion, which would be a pinhole. Remember, this is all gradual change in evolution. Right, let's see if we can see your hand again, Bryson. Now I can see a rather precise picture of Bryson's hand. It's not a very bright one, but I can see every finger clearly delimited. So I could see, if I were this animal, I could see my predator in some detail. There is an animal that has a pinhole camera for an eye. It's a mollusk called nautilus. It's a relative of the octopus, but it lives in a shell, and there is its eye. Just has a simple hole, and seawater can flow in and out of that hole. Here's a shell of nautilus. This bit of rock here shows ammonites, which are a now extinct relative of nautilus. They were once immensely common, as this rock suggests. I like to think of all those 100-million-year-old dramas that must have been witnessed through the pinhole camera eyes of ammonites. We can't be sure they had pinhole camera eyes, but it seems quite likely. Now, a pinhole camera is not a very good way of seeing. It does produce a sharp image, but because it's so narrow, you hardly get any light in. The answer to this problem is that ingenious device, the lens. Nautilus has a pretty poor eye compared with its relatives, the squids and octopuses, because they do have a lens. And so we can't help wondering, why doesn't Nautilus have a lens? Why didn't it evolve a lens? Well, I suspect that Nautilus may have got itself stuck on a little peak some way up Mount Improbable. You see that although we've got one big peak there, there are various other peaks on the way. There are quite a lot of them. And since the rule in evolution is just to keep going uphill, when the ancestors of Nautilus came up the track here, up the path here, and got to this point, that way uphill looked just as inviting, so to speak, evolutionarily, as that way. Both of them were uphill. Evolution has no foresight. Evolution has no way of knowing that if you travel up that way, you're going to end up with a lens. For the moment, this appears to be a perfectly good way to travel, because the pinhole camera at this level of illumination is an effective eye. So I wonder whether perhaps Nautilus has got itself trapped on top of this little hillock and is now unable to escape, because escaping would mean going downhill into the valley, and the one thing you cannot do on Mount Improbable is ever go downhill.